Welcome to the course on FPGA-based signal processing systems. This is lecture 4, which would be covering DSP and integrated design suites. So, the digital signal processing has the basics of sampling, latency and pipelining. Also, the transforms like discrete Fourier transform, fast Fourier transform, discrete cosine transform, wavelet transforms and so on, which will also be included the filter structures like finite impulse response and infinite impulse response filters. Also the algorithms like adaptive filtering algorithms of least mean square and then recursive least mean square, also RLS recursive least square algorithms will be part of this digital signal processing part course, actually, which should cover these algorithms. We will see that how to implement them in field programmable gate arrays, and especially these DSP applications are wide, and it underpins audio and video equipments, also the wireless and wireline communications, medical diagnostic equipments. We can see them mainly in military systems. This list is not exhaustive, and to list a few, we have given this DSP areas, application areas. If we say take this DSP systems, mainly those are complex and its reliability mainly depends on the hardware and software architectures used in them. So, the development process and the verification processes also make this systems very important, and the maintainability of the design is also a factor. If we see the fundamental issue in the case of DSP is that the architecture what is preferred in the design, also the type of hardware platform which is used for the deployment of these DSP systems. Further, if we look at this DSP functions, which are implemented basically in two types of processes. One is digital signal processes, and then other one is the FPGAs. So, DSP functions can be implemented in DSP, that is the processors, and then the FPGAs. The DSP processors are specialized form of microprocessors, and FPGAs, we are looking into these lectures that highly configurable hardware it has. So, the digital signal processes, when we say this is very common processes, it is ubiquitous. Also the outstripping processing capabilities, it has huge processing capabilities, and especially when we talk about the processing capabilities, it is having the MIPS, number of millions of instructions per second. So how much is the MIPS involved in this? How many instructions per second the processor can process, makes it unique. Also it is specifically sequential programming, it's not the concurrent and any other software, so it's used sequential programming. So when we talk about FPGAs over DSP, these FPGAs are preferred over DSPs, and we have given a few list here. It's a MIPS requirement. Mainly if you compare DSP and the FPGA, the applications require mainly much millions of instructions per second. So when we compare it is better to compare with this FPGA and DSP with the MIPS, and its reliability. FPGA is more reliable and maintainable also according to the software development process and the application oriented things. So this FPGAs are also custom hardware architectures. If you look at the current FPGA layout, that is modern FPGAs, will have this high speed. First one is this high speed interfaces. We had seen in the previous lectures that we have the LUTs and the interconnects and IO blocks and the switches, and apart from that, these high speed interfaces, also this orange one which is shown here, high speed interfaces are coming up. Also the block RAMs here, you can see in the red color that black RAMs also placed in the layouts. Apart from that, there is a DSP block. The numerous new DSP blocks are keep on added to make this DSP functions implementable through this FPGAs. If we see the microprocessor is also part of this, and we have seen in the technology review that these blocks are getting added in the accumulation age. So this is the modern FPGA wherein high speed interfaces, BRAM and DSP blocks, also microprocessor, are part of this FPGAs. So when we have this DSP blocks, when we talk about that, these are dedicated high performance blocks, especially optimized for DSP applications. So DSP applications are mainly DSP blocks are included in the following series, like in Altera, Array, Static, Cyclone and Agilex series have these DSP blocks, and in the Xilinx there are these 7 series and Xilinx Ultra Scale Plus, all of them have these DSP blocks. So if it consists of this combination of dedicated elements, like it is dedicated to perform this multiplication, addition, summation, also subtraction, accumulation, also the dynamic shift operations. These are main part of this FPGA DSP blocks. So you have the number of multipliers included in this 9-bit multiplier or 18-bit 18 cross 18 multipliers. So these are the very special about this DSP blocks, which is used to perform the DSP applications or the functions to put it in the FPGA. So if you consider this FPGA as a black box, so we have it here, this block which has the clock and the IOs. These are the IOs present over here, and the registers and memory. If we just represent this as a block, the registers, and we have these connectors, logic and arithmetic units. It's a multiplier or adders. So these are all the resources available in this FPGA after performing this place and route, the verification and so on. So we are going to look at the process, how this integrated suits from the design to the final stage of verification and place and route. So after performing all these operations, that if you look at this FPGAs, the input, suppose it's taking this as this registers are delays and this is the input line. The connector is used for this. A connector is picked up and connecting it from the input to the multiplier and registers. These are the registers placed and multipliers and the adders. So often this multiplier also will have the another input which can have which will be the coefficients or in case of filters. So there are multiple the inputs can be added to it. So this is placed nicely in the FPGA. So this is how these DSP functions are used. Our DSP functions are implemented inside the FPGA. After initially it looks like that, and then after completion of the task it would appear like the nicely placed filter in this case. So now coming to the comparison between these DSPs and the FPGAs, that is the processors. So this DSP processor has this external memory, PL, phase lock loops, clock reset, and then have this peripheral IOs, DMA engines, direct memory access engines, and memory, stack, cache, and data access addresses, generators, DSP core, RTOs, scheduler, and then interrupt service routines. So there are threads. The task to be performed here, it is called as thread. The 1, 2, 3, 4, 5, 6 threads are available in this is a block diagram of this digital signal processor, and we consider only this software developments of the process. These are these resources which are available in the DSPs are shared by the thread or the task. That's what it is shown in here in the diagram. So these tasks, I have there is no isolation of OS for the particular task. So it is sharing all the resources whatever is available. So there is a much interaction between this resources, also the thread, the task, which is suppose 1, 2, 3, 4, 5, 6, those are all using these resources. So there will be much interaction, high bug risk, and there is not much isolation. There is zero isolation in these cases, DSPs. Whereas FPGAs have the dedicated resources per task. So this has the pipeline style for flow. Also, if you look at this, so it is more reliable and the less need for the field updates. So often the updates of the software for FPGAs are not frequent, and in case of DSPs the software release it's frequent because of many reasons. So we're not getting into the much of the DS things. The FPGA architecture, if you look at the similar way fashion, so there is a top level file and external data and control F, also the PLL, clock and reset. You can see the task 1, 2, 3 and 4, and which has the memory, DSP, IOs, and also the each task has the IOs, dedicated IOs, memories and DSP blocks. So that's the difference between this DSP and the FPGA. So where they are not sharing the resources, they have the separate DSP and memory blocks and IOs for it. Of course, this task, a well defined interaction between the IOs are used in this FPGA architecture. So the task split across independent logic. Each logic is handled by the different task here. So it's an independent logic. Also, we have, as I said, this dedicated memory and IOs are present in that. So the code is like this assembly language, which improves the style of coding, execution, as well as this throughput also. So because it's a dedicated resources for each task, the crosstalk between the interference is less. So the interaction between the task is if it is really needed, then it is performed. Otherwise, it is not. So whereas in the DSPs, that is the drawback, that the interaction is more and the high risk of bugs. So now coming to the integrators. So with this brief introduction about the DSP, as the course progresses, that we will also look at much examples of the DSPs and how these can be implemented in the FPGAs. Now moving on to the integrated design suites which are available for us with the FPGA. So this is the text editor, which is having the integrated design suites contain a text editor. So where you will be writing the codes, that is HDL codes, that hardware description language, either it is a VHDL or Verilog. So we can write, edit and save this program in the text editor. Also the compiler, which is responsible for passing the HDL program. So what you had written as an HDL code, we have the compiler which finds it, goes through it, understands it or interprets the code, finding the syntax error, also the figuring out what program says. So if there is any syntax error, immediately it shows up that there is a syntax error, and it interprets the language or the code what is written. So that's the function of this compiler. So text editor we have in the integrated design suites and the compiler. The next one is the synthesizer, makes this the compiler, whatever the output of the compiler, it makes it suitable or targets the design, whatever the design you have to return in the editor, to a specific hardware technology. This technology can be FPGA. For us, we are looking at here this FPGAs. So this is programmable logic devices or complex programmable logic devices, PLD and CPLDs. Also the application specific ICs. These are all using this integrated design suites. So for our focus is that FPGAs. So it targets the design specific hardware technology. So the synthesizer decides this which FPGA will be used for your design. And then there is a simulator in the integrated design suites that it takes the input from the again the HDL program, that is a Verilog program. It takes what is the input for my design. Suppose I just design an AND gate and I want to give the inputs are A and B and the output is C. So as an 1-bit input and inputs, and the output is a 1 bit. So these inputs are to be specified in another Verilog program which is called the test bench, and that is the inputs are taken to the simulator and the time sequence inputs, and then that is given to the output is decided from the simulator, depends on the functionality what it has. And then the test bench sequence can be it is another HDL program. So as I said, the Verilog, the inputs which are needed are to be put in the Verilog code, and then it is written in that same language, either the VHDL or Verilog. So the test bench is the number of inputs which you want to test it for the design what you have. Either it can be an AND digital circuit of simple AND gate, or the decoder or multiplexer or your filter in the DSP. So those inputs are put in the test bench and in a time sequence manner, and then those inputs are given to the design through the simulator, and then the function of this design is verified and the outputs are visible to them. The outputs are taken. So these outputs which are taken can be viewed graphically using the waveform editor, or it is described with the And this is the tool waveform editor, where you can see the output of this for this particular change in the input. Suppose in the AND gate, as we said, the A and B are the input and the output is C. So if you change the input A and input B at some instance of time, and then the corresponding change in the output can be viewed through this waveform editor. So it has a waveform editor. So you have the text editor and the compiler, and you have the synthesizer, also the simulator, and the test bench is part of the integrated design suite, also the waveform editor. Now if you look at the simulator is as I said, the input sequences, the combination of inputs, all inputs, what are the inputs can be possible, whatever the possible inputs can be given in the test bench and given to the simulator. So the hardware internal signals, and also the based on the input, the simulator decides this output, the internal signals as the time specified in the input. Suppose A input is existing for some time 1, and then it is changing to 0. The B input is initially 0 and then it is changed to 1. So what is the corresponding output in C? Okay. So the specified period of time, the change in inputs will be determined by the simulator. And the output of the simulator, as I said, that it can be viewed in the waveform editor. Also the output can be even viewed as a text in the console itself, as the integrated design suite console. We can see them, if there is any, what is the output, and any error message or warning messages related to your code. If there is any kind of unusual conditions, so all will be listed in the console also as a text file. That is a possibility. So integrated design suites have the simulator and waveform editors to view the output as well as give the input in this design suites. So the template design suite, to make it easy for the user, there is a template generator. So the template generator, which is a text file actually, so it is giving the outline template of a Verilog code or .v file. Especially when we deal here, it is going to be a Verilog codes in this course, and that will be saved as a .v file. That's a Verilog code. So it's a text file. In the template generator generates a text file in which the outline is commonly defined. I mean that the program structure. So in Verilog code we have this module, end module, and then what is the module name, and what are all the inputs, and then depends on what you give, you can fill up the blanks, and what are the input and output declarations, and what would be the statements you would be writing. The statements will be kept blank in the template generator. That is the code which you are going to write. Maybe for example, the logic structures of the decoders, adders, and the registers also can be generated in this case. So if you give in the template, if you give the number of inputs, what is the bit size of each input, and what is the bit size of the output, and then it generates a template. The suites, integrated design suites, generate a template for your code as well as for the test bench. So the test bench also can be generated using the template generator. So the schematic viewer is also part of this design suites. It creates this a schematic diagram which is corresponding to the HDL program, that program what it describes. So there is a blocks, these blocks are connected. So it depends on the code. This schematic viewer shows the blocks which are needed for the program, and it shows the intermediate language output of the compiler. So after the compilation output, you can see the blocks connected, which is equivalent to the design what you have done in the paper, like your digital circuit. So the translator, which is the next one, the template, schematic viewer, and then the translator, it targets the compiler intermediate language output to a particular device which is FPGA. So it gets translated into the diagram what is given by the output of the compiler, and takes the FPGA resources. From the resources, what are all the, suppose for in the logic blocks we have this LUTs and the flip flops and mux. So what are the things needs to be used for your designs? Okay, so this is decided by this translator. Also it finds it out from the resources, and which fits the translated the number of LUTs required, and the and the flip-flops required, logic elements required, or the number of slices in terms of slices. These are translated ones are from the available resources are getting fit into the FPGA. So that is, it chooses them through the programmable interconnects and the logic blocks what we have. So for the given FPGA, so your design requires what are all the resources. It is decided in the fitter. So always your code should be in such a way that it should fit your design in the chosen FPGA. So if it doesn't, if the content doesn't fit, or if your program is needed more resources, like the number of multipliers and the logic elements are more, then it will immediately say the design doesn't fit into the device. So we have to reprogram it if the device is fixed. If you are not going for the larger FPGA, then for the fixed device, FPGA device, then you need to go for the design change in the design. So the chip viewer, so after choosing this logic blocks, interconnects and all those things, how your chip, which is going to be manufactured chip, how it will looks like. So that is what the how it will look like is the given for the designer in the chip viewer. The design has been laid out in the chip. So how this chip would be looking like. So that is given by this chip viewer, is also part of it, and the timing analyzer, which is very important when we try to implement the design in the FPGA. So this timing analyzer takes all the paths of this input to output and find out the delays in that path, and also find the critical paths, maximum path, how much, what is the delay in the path, and which is matching with the clock or not. With the given clock, these delays can be handled or not. So this timing analyzer looks at all the ways of the signal paths and then figure out that what are the delays involved in the design. So back annotator, if according to the timing analyzer, suppose this is certain path requires some more delay, the design gives the timing analyzer gives the details of the delays to be inserted in the particular path. Also, if there is any lack of delay comparing to the other paths, so it inserts the delay class statements in the original this HDL program, and again the corresponding delays are being calculated using the timing analyzer. So the back annotator does this job of inserting the delay. So we have this thing that template generator, schematic viewer, and then it goes to the chip viewer, fitter, timing analyzer, and back annotator. So now if we look at the design flow, so with this background, that we have the code, which is the block diagram, the hierarchy or the block diagram. So you have the design with you in the paper, that you have designed the decoder or the multiplexer or the filter design, any of the digital circuit here. So we take that block diagram that is in the paper. The first block which shows over here is what is the hierarchy in which that diagram should be implemented. So the block diagram is shown over here, and then the corresponding code you will be writing, that is the HDL code. It's a Verilog code here in this course, that Verilog or VHDL. The VHDL, we are not dealing with this, but Verilog codes we will be writing in this. That is the next is the coding part. So according to the design what you had done it in your paper, and that should be translated into code, the Verilog code. So after that coding, that code is compiled. And the compilation, finding the syntax, and then what is the code says, that the understanding or the interpretation of the code is done by this compiler. The compilation is done, and then it is going to the simulation. So before getting into the real-time device, the FPGA, so these code is simulated using the simulation, and then the verification is also a part of it. Here we do this functional verification without considering any time delays in the path. The timing part is ignored in this verification. The verification has these two types, again functional verification and timing verification. So the simulation is done, so functionally verified whether the AND gate what I designed is doing the AND gate job or not. Okay, so that is done in the simulation. If that is, if the function is could not be verified at this stage, suppose we have at the coding stage we have this there is an error that if you, before getting into the compilation, if you yourself find and go and change your design. So that's the path which is shown over here. So you have to change the hierarchy and so on. Also, after this compilation, if there is any syntax error or anything, compiler find that, then again change the block diagram and this coding part here. So here next is coming to the after the coding. So if in the functional verification it could not be done, so the function which needs to, the design needs to be giving the output is not, you are not getting that through the simulation, and go and change the design over here at this point. Okay, so the each stage we can have the verification, or we can go back and check that initial stages, and at any point of time that you can change it, and then in the process you can redo the things. So if there is a syntax error after the compilation, go and check this coding and change the code syntax error, and then again compile it. And then if there is a functional the verification failure, or the simulation is not giving the output, and go and change this here again the coding part, and then remove that what is the functionality error here is. So this is going to be the front end steps which is to be done, which is being performed in the case of the design flow, HDL design flow. So after it is done, then we come back to this backend stage where this is about the simulation part. Until then, we know that the code what you have done, you have you use it in the Verilog code, you compile it and then see that this is how giving the output. After that after that the simulated code is to be dumped into the FPGA, field programmable gate array. So what is the process involved in that? So the 3 easy steps here shown, and the details of it will be covered in the course that were in the I mean some of the subsequent lectures. So here is the simulated input, the code which is given to the synthesizer block, that is synthesis, which converts that, which is looking for the hardware here, the resources available in the FPGAs. So according to your design, what is the resources required? It is the interpretation, what are the resources required is said, and then it is fitting place and route. The place and route is selecting the program interconnects and which route it should be followed, which logic block should be used, and whether the design is fitting in the chosen FPGA. So that is the fitting or the place and route block in the design flow. After that it goes for the timing verification. So far in the verification we have done only the functional verification. Here it does the timing verification, meaning it involves the delays in the circuit, or then the digital circuit. It designs, so checks for all the path delays, and the actual delays are included, and then the verification is done once again. So after this verification it is ready to get the deployment. So but the output of the timing verification, suppose it is not, it is giving some error, there is a time delay. If it is error, and it should go to the change in here, either the coding part, or again it should go and change the design itself. So there is a two-way process, and if that design is again also can check through this before timing verification, is that place and route, there is any error here, or in the synthesis the hardware itself the realization is not okay. So this point the error when the error is appearing, it becomes it needs to be taken care. So this is the backend step. So the synthesis, fitting, and or place and route, also the timing verification. So when the error occur, if there is a change in the code and other thing, coding only, that's okay, that is common, and I mean we can change it, at the stage that what is the change needed in the code. But if it takes the design to be changed, it's not fitting, or it's not the timing analyzer is not available. So here it's after fitting also it may say that the design doesn't fit. So either we can change it in the code, change the design in the code, or the design itself. So there is a multiple paths here from this fitter output, and then the timing verification also. So that we have to go and change the design here. So according to the FPGA has been chosen, or we have to choose, if this is a fitter problem, you can choose this different FPGA, that larger FPGA which can fit your design. So if there is a delay and the other timing verification is yes, it should go here and change the output of the block diagram, the coding part. So coming to the front end, yes, there is a front end. It is trying to figure out the basic approaches and the building blocks, what you have done at the block diagram level, that is pen and paper thing. After that, the logic designs, the larger logic designs, what is the hierarchy, it decides the hierarchy in which this block, your design should be done. Also the VHDL and Verilog, they give this some defining modules, their interfaces even. So if we coming to this the HDL codes for the modules, also there are interfaces and the internal details are required for writing the HDL codes. We have this HDL compiler, checks for the compatibility and syntax errors. The simulator allows your design as many inputs as possible, and it's a part of the verification. As I told you, there are functional verification and timing verification. So functional verification just study the logical operation whether it is correct or not without considering any timing considerations. Here is the gate delays and other timing parameters are completely avoided, are considered to be 0. And in the case of timing verification, yes, this estimated delays, what is the setup time, hold time, record for flip-flops, and all of this is especially in the case of sequential circuits. So the devices of sequential devices needs the setup time and hold time, and estimated delays are also considered in the timing verification. So the backend, it is to convert this description into the components. As I told you, the resources of the primitive are hardware components for the technology targeted. The fitting allows this device the resources, whether what is to be chosen or it is a mapping, and then it is after this post fitting actual delays or all of them are considered. So it is calculated with all the timing delays, and some functional inputs also is given at this stage to verify that whether the design is proper or not after post fitting event. So the features are again, it can be the hierarchical design. The design can be hierarchically decomposed. What is the next, what is the module, and so on. So also each design can have the interfaces, input, output, and functional specification, etc. Precise functional specification also. You can have this specification. It can be of different types, like this. One is the behavioral or structural, or it is a data flow. It depends on, there are 3 types again, we will be looking at it. So these functional algorithms also is possible, functional specification is possible to give it. Also the concurrency, timing, clocking, everything can be modeled in this using the design source. So it also handles the synchronous and asynchronous sequential circuits with the structures possible. Logical operations with the timing behavior can be simulated. Thank you.